Hello! In this video, we're going to prove the intermediate value theorem, which says the following. Let f be a function from the closed interval a comma b to r, and f is continuous on a comma b. And suppose w is a real number such that f of a is less than w is less than f of b. Or we can have f of a greater than w greater than f of b. Then there exists an element c in the open interval a comma b such that f of c is equal to w. Now, in proving this theorem, we are going to be using the concept of partitions of an interval. So if we consider our closed interval a comma b, well then a partition of a comma b is a collection of non-overlapping closed intervals whose union is a comma b. So for example, this collection of closed intervals would be a partition of a comma b. And we might label these intervals I1, I2, I3, I4, and I5. And we might label the endpoints x0, x1, x2, x3, x4, and x5. In general, we can label a subinterval II by xi minus 1 comma xi. Now a tagged partition is when we select a point from each of these subintervals. And let's say that the points that we select are these. Each of the points that we select are what we call tags. And we might label the tags T1, T2, T3, T4, and T5. And the way we symbolize a tagged partition is by a letter with a dot on top. And the collection is essentially the collection of subintervals along with the tags in each of those subintervals. So just like this. So now, let's talk about what a gauge is. A gauge on a comma b is a strictly positive function defined on a comma b. For example, the function defined by delta of t equals t squared plus 1, where t is any element of a comma b, would be a gauge on a comma b. Now, given that delta is a gauge on a comma b, and p is any tagged partition of a comma b, then we say that p is delta fine if the following is true. We say p is delta fine if each subinterval of the partition is a subset of this interval, which is an interval centered at the tag of the subinterval. So the way we can visualize this is if we consider our subinterval II, and we'll say that the tag of our subinterval ti is right here. Well then, this interval is an interval centered at the tag ti, and its radius is delta of ti. Or in other words, its radius is precisely the output value of when you send a tag ti into the gauge function. So this interval might look something like this. And so for p to be delta fine, we need each subinterval to be a subset of this interval. So for example, for this partition to be delta fine, we would need I1 to be a subset of this interval centered at T1. We would need I2 to be a subset of this interval centered at T2. We would need I3 to be a subset of this interval centered at T3, and so on for each subinterval in the partition. Now, a result that follows is that if delta is any gauge function on a comma b, then there does in fact exist a partition of a comma b that is delta fine. And so these are the ideas that we're going to be using in proving the intermediate value theorem in this video. Now, another result that we're going to be using in this video is as follows. Suppose n is an integer greater than or equal to 2, and a and b are sets. If 1 is an element of a, n is an element of b, and each integer between 1 and n is an element of a or b, then there exists a pair of adjacent integers, j and j plus 1, between 1 and n, such that j is an element of a and j plus 1 is an element of b. So a way that we could visualize this result is as follows. So you can imagine we have a path of points labeled 1 through n. And let's say that we know that one of the endpoints is red, while the other endpoint is blue. Now let's say we're given that every point in the path is either red or blue. Well then, this is enough information to say that there exists a pair of adjacent points in the path, I'll call j and j plus 1, such that j is a red point and j plus 1 is a blue point. And so that's a way of visualizing what this result is saying. Okay, so now let's get into proving the intermediate value theorem. Now we're trying to prove that there exists an element c in the open interval a comma b such that f of c is equal to w. And to prove that, we'll assume for a contradiction. Instead, there doesn't exist an element c in the open interval a comma b where f of c is equal to w. Well, in that case, we know that f of a and f of b aren't equal to w. So this further tells us no output value of the function f is equal to w. Now, since f is continuous on a comma b, this means that f is continuous at every point in a comma b. So if we consider an arbitrary point t in a comma b, well then we know that f is continuous at t. And by definition of continuity, to say that f is continuous at t means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in a comma b, where absolute value of x minus t is less than or equal to delta, we have that absolute value f of x minus f of t is less than epsilon. Now, an equivalent definition has this as a strict inequality, but it's perfectly fine if we have a weak inequality here, because the definitions are equivalent. So since f is continuous at t, this means that this statement is true, and this statement works for every positive real number. So in particular, it must work for the positive real number absolute value of f of t minus w. Right? We know that no output value of the function f is equal to w. So that's why absolute value of f of t minus w is greater than 0. So taking epsilon to be absolute value of f of t minus w, it follows that there exists a delta greater than 0, such that for all x in a comma b, where absolute value of x minus t is less than or equal to delta, we have that absolute value of f of x minus f of t is less than absolute value of f of t minus w. So what this shows is we can map each element t in a comma b to a positive number which satisfies this statement. So we can treat this as a function, mapping each element t in a comma b to a positive number delta of t, which satisfies this statement. Now the claim is, if we consider an arbitrary element x in a comma b, where absolute value of x minus t is less than or equal to delta of t, it follows, if f of t is greater than w, then f of x is greater than w. If f of t is less than w, then f of x is less than w. So to prove that, let's consider an arbitrary element x in a comma b, where absolute value of x minus t is less than or equal to delta of t. And from here, we want to show if f of t is greater than w, then f of x is greater than w. If f of t is less than w, then f of x is less than w. So let's first suppose f of t is greater than w. Now we know since x is an element of a comma b that satisfies this inequality, then no matter what, it follows that this inequality must be true. So in the case f of t is greater than w, we must have absolute value of f of t minus w equal to f of t minus w. So this becomes absolute value of f of x minus f of t is less than f of t minus w. Now, the absolute value of any real number is equal to the absolute value of its negative. So the absolute value of f of x minus f of t is equal to absolute value of f of t minus f of x. So we have this, but then every real number is less than or equal to its absolute value. So in particular, f of t minus f of x is less than or equal to its absolute value. So this shows f of t minus f of x is less than f of t minus w. So subtracting f of t on both sides, we're left with negative f of x is less than negative w. So then multiplying negative 1 on both sides, that leaves us with f of x is greater than w. So this shows if f of t is greater than w, then f of x is greater than w. Now let's show if f of t is less than w, then f of x is less than w. So we'll suppose f of t is less than w. Well, then in that case, the absolute value of f of t minus w is equal to w minus f of t. So this becomes absolute value f of x minus f of t is less than w minus f of t. But remember, every real number is less than or equal to its absolute value. So in particular, f of x minus f of t is less than or equal to its absolute value. So this shows f of x minus f of t is less than w minus f of t. So adding f of t on both sides, these go away, so we're left with f of x is less than w. And so this shows if f of t is less than w, then f of x is less than w. So putting this all together, what this shows us is for each element t in a comma b, we can find a positive real number, delta of t, with the property that for all x in a comma b, where absolute value of x minus t is less than or equal to delta of t, if f of t is greater than w, then f of x is greater than w. And if f of t is less than w, then f of x is less than w. So we're mapping each element t in a comma b to a positive number delta of t with that property. So delta of t is a positive number defined for each element t in a comma b. Therefore, delta is a gauge on a comma b. And since delta is a gauge on a comma b, we know that there exists a delta-find partition of a comma b. I'll call that partition P. And we'll label the subintervals of the partition by II, and we'll label the tags by TI, from I equals 1 to n. And we're going to write each subinterval II as xi minus 1, comma xi. Now, to reach a contradiction, the idea is to consider the following sets. We consider the sets A and B, where A is the set of integers I between 1 and n, such that f of x is less than w for all x in the subinterval II. And B is the set of integers I between 1 and n, such that f of x is greater than w for all x in the subinterval II. Now, let's sort of get a visualization of what it means to be an element of these two sets. To be an element of A means that every output value on the subinterval is below the line y equals w. To be an element of B means that every output value on the subinterval is above the line y equals w. Now the claim is that every integer between 1 and n is either an element of A or an element of B. So to prove that, let's give ourselves an arbitrary integer I between 1 and n. Now we know that no output value of the function f is equal to w. So in particular, if we take the tag ti and send it into the function f, well then its output value is not equal to w. So either f of ti is less than w or f of ti is greater than w. What we're going to show is if f of ti is less than w, then every output value on the subinterval ii is less than w. And if f of ti is greater than w, then every output value on the subinterval ii is greater than w. So let's first consider the case f of ti is less than w. To show that every output value on the subinterval ii is less than w, well, let's consider an arbitrary element x in the subinterval ii. Now, since this partition is delta fine, we know that ii is a subset of this interval. So x lies between ti minus delta of ti and ti plus delta of ti. And by properties of absolute values, this is the same thing as saying the absolute value of x minus ti is less than or equal to delta of ti. But then, let's go to the definition of our gauge function. Replacing t with the tag ti, well then delta of ti is a positive real number such that this statement is true. So if we take x to be the x we have in our proof, well, we know that absolute value of x minus ti is less than or equal to delta of ti. That's what we have here. And we're working under the condition f of ti is less than w. So that implies we must have f of x less than w. So this shows if f of ti is less than w, then every output value on the subinterval ii is less than w. So that would show I is an element of A in this case. But now let's consider the case f of ti is greater than w. Well, in that case, if we consider an arbitrary element x in the subinterval ii again, well then, since the partition is delta fine, we would have that x lies between these two values, or in other words, we have absolute value of x minus ti less than or equal to delta of ti. But in this case, again, going back to the definition of our gauge function, in this case we have f of ti greater than w. So that implies f of x is greater than w. So that's what we get. So this shows if f of ti is greater than w, then every output value on the subinterval ii is greater than w. So in that case, we have I as an element of B. So no matter what, whether f of ti is less than w or f of ti is greater than w, this shows I is either an element of A or B. But we can never have an integer I that's an element of both A and B. Because if that were the case, then every output value on the subinterval ii would be less than w, but also every output value would be greater than w as well. And that's absurd. So yeah, no integer can be both an element of A and B. So what we're essentially doing here is we are setting ourselves up to apply this preliminary result. And what we've essentially done in this paragraph is we verified that the third condition is true. So since every integer is either an element of A or B, then in particular, 1 is an element of A or B. In other words, it's either the case that every output value on the subinterval I1 is less than W, or every output value on the subinterval I1 is greater than W. Well, we know that f of A is less than W, and A belongs to I1. So, since we know of one output value on I1 that is less than W, well then every output value on I1 must be less than W. Similarly, we know that n is either an element of A or B. which means either every output value on in is less than w, or every output value on in is greater than w. But we know of one output value on in that is greater than w, namely f of b. So since f of b is greater than w, we must have every output value on in greater than w. So n is an element of b. And so that verifies that these two conditions are true as well. But is n an integer greater than or equal to 2? At this point, n is only greater than or equal to 1 for all we know. But since 1 is an element of a and n is an element of b, that tells us it can't be the case that n is equal to 1. Because if n is equal to 1, then that implies 1 is an element of a and 1 is an element of b. But that contradicts the fact that no integer between 1 and n can be both an element of a and b. So yeah, n can't be equal to 1. N must be greater than or equal to 2. So that verifies this holds as well. So we satisfy all the premises for our preliminary result. So we can conclude that there exists a pair of adjacent integers between 1 and n. We'll call them j and j plus 1, such that j is an element of a and j plus 1 is an element of b. Well, since j is an element of a, this means that every output value on the subinterval ij is less than w. Since j plus 1 is an element of b, this means that every output value on the subinterval ij plus 1 is greater than w. But remember, ij and ij plus 1 have a point contained in both of them. So this is ij and this is ij plus 1. Well, remember how we're labeling each subinterval. This must be xj minus 1, this is xj, and this is xj plus 1. Both ij and ij plus 1 share the point xj. Since xj is an element of ij, that means f of xj is less than w. Since xj is an element of ij plus 1, that means f of xj is greater than w. So we have a contradiction. Our assumption that there is no element c in a comma b such that f of c is equal to w leads to a contradiction. So we must instead have that there does exist a c in a comma b such that f of c is equal to w. And so this completes the proof. Now, if instead you were given f of a is greater than w greater than f of b, well then you have basically the same argument. It's just instead, up to here, you would instead have 1 is an element of b and n is an element of a. Well then in that case, the integer j that you identify will have j is an element of b and j plus 1 is an element of a. But you still reach the same contradiction. And so yeah, that's pretty much it for this video.